Well, hello friends. Welcome back to the program. Today we are going to work on the profiler, and I have a new feature in mind. So it's something that we'll be borrowing from Apple's Instruments tool, and it's this thing called top functions. And I'll show you, let's just grab a profile of something here. So this is the JavaScript test suite. And normally what we see here is just the plain root of each sample. And most of the samples you can see 689 out of, I don't know, 700 start in _start, which calls main. It's very typical. The reason that some samples start in another call frame, which you would expect below main, is because we have a limit on the number of frames captured. So these actually should have main and _start in the call stack, but because of the limit, you can see here that they're quite deep, right? So because of the limit, I think it's 32 frames or something like that, they end up starting at some other frame. Anyway, so the thing we have right now to manipulate the call graph is we have inversion on Control I, and what that does is that it flips the graph upside down, or inside out, if you will, so that the innermost frames become top level, and then you can look at these innermost frames and see, okay, well, who's calling this, and then who's calling that, and so on. You can like sort of work your way backwards. But there's this great feature in Apple's Instruments, which is called top functions. And what that does is that it takes every one of these functions here that participate anywhere in the graph, and it makes them into top level items. So I guess the easiest way to show you what I mean is by just making a simple call graph here. So imagine that we have, I don't know, like we'll make up a stack here. So main calls a cold function 1, which calls a hot function, which calls a worker function, or yeah, something like that. And then you would have, and this is stack sample 2 and 1, and say that you have cold func 2 instead of cold func 1. So our graph for this, the normal graph, would be something like this. Like that, right? Let's see. And in such a small contrived example, obviously this is like easy enough to get an overview. And I guess just for completeness, let me show you what it would look like upside down. So that would be worker called by hot func, called by cold func 1, cold func 2, and both of these guys are called by main. So this new thing that I want to build today, this is, let me just label these: normal, inverted. So what I want to do now is top functions. And what that does, like I said, it takes the frames and makes every frame a top level item. And this is super useful when you want to figure out where is the time really being spent, like which functions dominate despite you calling them from different places. So if you have something that you call from many different places, and that will dilute how much it appears to be called in these things. So say, for example, in our case, the hot func, right? The hot function here is very, very popular, and just as the worker. Maybe we don't need the worker really, but let's just keep the worker anyway. Hotfunc, we want to see that hotfunc is the place to look for optimizations, right? Because coldfunc1 or coldfunc2, that's not really the place to optimize. The place to optimize is here. So what we want is we want a graph that looks more like main and then hotfunc. And basically, what this thing tells us is that everything is below main and most is below hotfunc. So then the graph would look something like this. So main, I mean, actually it would just be the normal graph under here. So coldfunc2. And under hotfunc you would see worker, and then I guess you would get, probably get worker, and then coldfunc1, coldfunc2, something like that. Essentially we take this graph here, but every time that we encounter a frame, we also make it a top level frame. So, and then we fill in the graph, the tree underneath those frames. I hope that I'm making sense with this explanation. Now, I've only ever used this feature. I haven't really tried to implement it. So this is just my understanding of how it works. There might be some detail that I'm getting wrong, but I think if we just implement this, then we should be able to see some interesting stuff. And actually, let me show you what is kind of annoying about the current state of things. Because here, if you look at this JavaScript test suite profile, and we go into interpreter run, like most of this action happens below here, right? Which calls interpreter execute statement. But further down the stack, you might find execute statement again, right? But because these guys are at two different levels in the same stack here, and they're being called, this guy's being called by script function call, this guy's being called by program execute. There's no aggregation of the fact that we are spending a lot of time in interpreter execute statement. So the purpose of the top functions view is to aggregate those at a top level so that you can identify your real top functions. Okay. So that's enough of me talking about that. Let's try to implement it. So this would be in the profile class. I guess, well, we'll want this to be a mode actually, wherever we set the inverted flag thing. So we'll top functions. We definitely want this to be an optional mode, not shouldn't be the only way that you identify things. So where is the invert tree? Okay, so just setting up some UI for this here. Let's do that right away. Call this top functions, and Control T seems good. Top functions action. Set top functions, that's a really crappy name. Show top functions. Slightly better. Yeah, show top functions, it's cool. Okay, and then when you call show top functions, and then we rebuild the tree. Cool. So the profile class, the way that it works is that it has a tree of profile node objects. And whenever you change the settings of the profile viewer, then we throw away the profile node tree and just reconstruct it based on the sample buffer. And the sample buffer is just a long vector of captured stacks. So essentially profile viewer, or the profiler as it's now called, the bulk of his job is to just take a vector of call stacks and aggregated them into an interesting tree. So let's see. So that would be, is it load from perf core file? No. The profile constructor, I forget where things are. Oh yeah, it's in rebuild tree, of course. That's what I was calling. Okay, so rebuild tree. So there, blah, 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 and here is the main loop here that walks over all of the events, as we call them. An event is, in the case of a time profile, the event is just a call stack. And there's also support here for memory allocation profiles, in which case an event is a malloc or free. But right now we care about time samples, so those are just call stacks sampled at a regular interval. Those are our events. So let's see, so blah, blah, blah. If here we're filtering, like you can filter the time range by selecting here. So that's the first thing we do, is we just check if the event that we're evaluating is within the filtered range. Otherwise we exclude it from the tree. Or from the tree, I guess. Okay, and then here's a lambda. And then we iterate the frames in the event. So each one of these is a frame. So we're walking all of those here. And for each frame is this helper here, which walks backwards in case inverted mode is requested. So that's pretty straightforward. So let's see. So I think this will be our normal mode. So if not show top functions, then we do it the old way. Else, I don't know why the auto indentation in my editor is not working, but that's fine. So how do we go from this to this? I guess the easiest way would be to simply do a nested loop here. So instead of walking the frames like this one at a time, we would do a two-level loop. So let's see. No, we have the event. Frames at I. Oh no, size. Right. That's so weird that the auto indentation is. Well, now it started working. That's so weird. Okay, so then J, but we will start J at I. Okay, so then we'll do we'll do a nested walk so that we get. First we get worker, then these, and so on. Okay. So, frame is event frames at J. And then we can do kind of the same stuff as up here. But if symbol is empty, which means that we don't have a name for that frame, so at that point we can just stop iterating. Wait, does that mean we should stop iterating entirely or just here? I think we'll just break out from the inner loop here. Okay, so then we check if we have a node. Wait, what is the node? Profile node. So let's see, let's put that here. And manage it for ourselves. Okay. So if we don't have a node, then we need to either find or create a root, right? Yeah, right. So we have to create a root node if we don't have one already. With these inputs. So same as above. Otherwise, we find or create a child in the currently open node. Yeah. So this sort of recursion is how we build up the tree. That makes sense. It's been a while since I looked at this. I wrote this profiler originally in a video. If you want to go check it out, it's called something like "Let's Create a Profiler for Serenity OS" or something like that. If you're not super familiar with profiling, but it is pretty straightforward. Okay, and then we're kind of doing the same stuff as above here, right? So essentially, we want to bill 1 unit of time to the currently selected node, and then if this is the innermost frame in the event, then we want to bill 1 unit of self time here. So that would be if j is event frames size -1, then it is the innermost frame, and we can say node increment self count. So that feels vaguely like this should work. Let's see. Oh, let's make a profile of something. Test.js. Okay, and moment of truth. Oh, shit. I forgot to invert tree. I forgot to add the right action there. I added invert action twice. That's stupid. Okay. All right. Top functions. That doesn't do much. Rebuild tree. Wait, how am I messing that up? Doesn't do anything. I feel like, is this code even running? Let's do it up here. Also, we could save this profile here. Call it P. Show top func is true. But it doesn't really seem to change much. Oh, wait. Wait. I'm forgetting something. We need to create a new root. Right, so we need to reset this guy at every step. And we don't need to print that out. Yeah, right. So start with a null node every step through the event. Wait, oh. I wanted to save that profile. Okay, this is more interesting. Now it's actually doing something. Let me get root. Okay, so we can see now that the number of samples goes up dramatically, which is not ideal, because obviously we only have 697 samples starting in start, so we shouldn't really have 2,000 samples somewhere, so we'll have to change the way we count the samples. But basically, we can see interpreter execute statement bubbling up to the top here, which is interesting, because indeed, I was mentioning I'm browsing the tree or the graph that you can see this in more than one place, like this guy right here. I guess what we're doing right now is that we just, anytime that we encounter this, we are bumping this here, this root, because we come here and then we find this root and we insert it underneath there. So all of these immediate children here, like interpreter VM, will also be an immediate child of this guy right there. Yeah. Okay, so the basic concept is here now. It's just that the accounting is all wrong, because I don't want it to say 2,037 samples, because there are not that many samples. If we switch to percentage, we can see that we're over 100% of samples. So obviously that's not good. So I guess the issue is that we're double counting a whole bunch of things. And the easy way to avoid double counting is that we would just have we would keep track of the set of events that are in every root, and then we would only bill an event to a root if it hasn't already been billed to that root by another event, or we bill a frame to a root if it hasn't been billed by another event. Yeah, so each root needs to keep track of all of the events that have been billed to it. So profile node, we can just, what if we just give it a bitmap, like scene events or something like this. Yeah, something like this, scene events, and then no, not libgui, actBitmap. Okay, and then this here is where we are choosing a root. So then we would have something like bool is root. Is root is true. Oh, wait. Let's do it slightly differently. Let's keep track of the root. And here, we'll say root is node. Okay, so now we know the root. Because that means that we can check here if root scene event get event index we just have the event pointer here because we're iterating using range for. So event index. So cool. So now we have the event index, I thought. Wait, where did it go? Oh, that's the wrong loop. Dang it. Okay. Apparently we're iterating across the events already once before here to filter out the live allocations in case it's a memory profile. Anyway. It's a bit weird that we do the memory profile and the time profile in the same logic, but it is also nice that it just kind of works. So let's see. So now we have our root, and we know that the root, if the root hasn't seen this event before, then we will say we have seen this event, and then we will bill it. Or wait. True. Then we'll bill him, but otherwise, if this is not a root, I guess we can just bill it anyway. We just don't want to build a root. So or wait, that should be fine. So if node is not root, always do this. How does that feel? Okay, I need to save that frickin' profile this time. Let me do that right away. Okay. Oh, we died. Oh, the bitmap. We have to resize the bitmap, I guess. If root scene events size is not resize. What API does bitmap have? I have not looked at bitmap for a while. So let's see. You construct a bitmap with a size and a default value, or you call grow. Call grow, I guess. Wait, is that the only API we have? It's very weird. Bitmap create. I guess we can do that one. So bitmap create scene event size. Okay, so now we have main at the top. And we can go in here and until we find somebody who has some actual samples in the self. Can we find the sample? Where was it? Right here. Yeah, that's that one sample. So it's kind of interesting because when you do top functions, then you get the, I don't know what to call these, like the top root, like everything becomes a root, and then you aggregate each subtree under each root. So the same subtree occurs multiple times in this graph, right? Just once for every root where it's relevant. And it's interesting to see like stuff at the top of the profile with like no self time, like main, because we don't spend any significant time in main, but we do spend a lot of time in stuff called by main. Although, where's all the self time? Like you would expect. This looks weird, by the way. Why are these all the same symbol? That's clearly not the right symbol. Maybe it got outdated. Let's see. Incrementing the self count. So we always increment the self count if it's the innermost frame. So So I'm not sure. I feel like I'm doing something wrong, but the graph like looks very reasonable. I just I just feel like we should find the self samples at some point here. Let me get a new profile because maybe something is up. Okay, well at least we can see like real kernel functions here. This is called ASM entry. Yeah. So like this is what the kernel frames are supposed to look like. And this is kind of cool that it like pulls up the syscall entry point, and then you can see all the different syscalls that are being called by here, despite them being called from completely different places in the test.js program that we ran. Because they're all called by syscall handler, you'll find them right here. Increment self count, yeah. It's like the innermost here doesn't even have a 1. That's so strange. Because there's nothing below this. So why doesn't he get a 1? J. Also, wait, am I doing this right? I feel like this should be an else if, because I don't want to be incrementing it twice. That wouldn't be right. I'll just see that that comes out right. Yeah, so this looks very, very reasonable, right? Like you have 691 samples in main, but only 685 in underscore start. But if you go here and look at the way the profile is, as I was talking about earlier, we have a limited number of frames in our profile format. So there's a little bit of cutoff sometimes. That's why you end up with more frames in main, because we have 8 frames here in main that, or just one frame away from cutting off start. That's where the difference is. But where is the self time? I wonder. Okay, we are refilled. So, let's see if we can't recreate this situation here from my contrived example, just to verify that things are behaving correctly, because I feel like there might be bigger mysteries in the whole of the JavaScript engine profile that are sort of confusing me right now. So let me just make a, I guess, X CPP, where X is for extra contrived example. And there we go. Okay, so we'll do something like this. And then what did I have here? Let's just make this thing happen. Here we want to do some obnoxious thing, so I don't know, something like this. Wait, is that not going to work because of the volatile thing? Right. Okay, we'll get to that. Something like this, right? Maybe we'll no inline these just to be sure. And then try to build that. Complaints about the volatile thing, right? So what is that thing? Diagnostic. Yeah, this guy right here. I'll just turn off that warning. Okay, great. Wait, I feel like that didn't run for very long. Let's make it run a little bit longer, get some extra samples. Okay, 200 samples, that's good enough for me. So what does its profile look like? We have start main, cold func, hot func, worker. Yeah, so this is basically what I was drawing earlier, right? Normal tree here. This is exactly what we want to see. And if we invert it, we see inverted, we have worker here. Hot func called by cold func, both of those called by main. And then of course we have start, which I didn't take into account when making this text document. And then if we use top, we see hot, let's see, top functions. I was expecting to see main at the top. Oh, but these have the exact same number of samples, so that's fine. So we have hot func bubbling up to the top, which is exactly what I wanted. And then we do have all of the self count in worker, which is exactly what I expected. So I think let's not overthink this and worry about the JavaScript profile, because there's probably other stuff going on in there. Like here with this simple example, we can see that the behavior is correct. We see everything becomes its own root, and then we aggregate everything under each root. I should have just made this sample program from the beginning. It's just, I don't know why I didn't think of that. Makes it so much more obvious to see how this is working. Very, very cool. So it works. I like it. And I wonder if we can profile something fun. Like, I guess we can do some browser stuff. So let's run that request animation frame test. And then we will profile the browser for a while. Not terribly many samples. If we do a top, then yeah, I really like how this comes out. So you can immediately see here that most of the time is spent below GUI paint event handling, and it just pops right up like that. Otherwise, you would have to like drill into this, and you see like event dispatch, and then you have eventually you find your way to the paint event stuff. But boom, puts it right up here. And you can see the clear rect is actually, painter clear rect is actually pretty chunky. I guess that makes sense. And then layout document paint in the web engine. Well, I love profilers, and this feature is one of my favorites in Apple's instruments, so I'm really glad that we have it now here. We can definitely refine it further. We didn't get into inverting a top functions graph, for example, so it's something else that we should do. But I think this is going to be it for today's video, so we are going to make a commit first, though. So let me commit this first. Oh, this thing is ugly. We shouldn't just have a public member like that. Scene events, yes. So this thing, scene event. Get event index. Let's do something like this. Void did see event. Then we need to size this thing. So let's see, what's the natural way of doing that? These functions are only relevant for root nodes, let's say. Will track scene events. Okay. Yeah, and I guess we can actually, here we can say if scene event size is not event count. Wait, we don't know the profile type yet. Yeah, okay. Okay, that's a little bit better. A little bit more expressive, at least, what we're doing here. Okay. That works nicely. And filtering with top functions totally works as well. Very cool. So here's startup only. You can see that startup is mostly in file system read bytes, which is kind of interesting. So what happens if we only do this? Ploop. We see that we're in start. Main, blah, 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 blah. Okay, so you have to go pretty deep here before you spot that we are, wait, why is this so wide open? You have to go really deep before you find the file system read functions, I guess because we're paging in the executable as the program starts. So that's a really good example of something that gets hidden normally. So here, like when you go deep, you see that we are paging something in, it's the executable. And when you switch to top functions, that you see page faults just go straight to the top. So actually, that's like one of the best examples ever of how top functions can help you identify something that's going on in a profile, whereas otherwise it's like takes you a bit of effort to figure that out. What else do we have here at startup? Just parsing and stuff. Anyway, let's commit. Yep, and yep. Profiler, implement top functions feature. Like instruments app has. This view mode takes every stack frame and turns it into a root in the profile graph. This allows functions that have that are called from many places to bubble up to the top. It's a very handy way to discover heavy things in a profile that are otherwise obscured by having many callers. Yeah. Very, very cool. So this is going to be it for today's video, and I thank you all for watching. I hope that you saw something interesting here. Even if you are not using Serenity for development, maybe you're on a Mac and you're using instruments, I encourage you to check out the top functions feature there. It's very, very handy, and I'm glad that we were able to implement it. We're gonna test crypto. No, how does that work? I forget how it works. Okay, boom. What is the crypto test doing? It is doing unsigned big integer multiply without allocation. Extremely heavy. Divide without allocation, also extremely heavy. Some great opportunities for optimization here. Anyway, thanks for hanging out today, and I will see you next time. Bye.